All right, we're going to start this video off a little bit different. We're going to talk about how to graph polar equations. Now to do this, it's going to be very helpful to know what the graph looks like before we even get started. And there's really two categories of graphs we're going to look at. The first ones are called Lemicons. That's going to be in our first row here. And those are always given by the equation, as we see up here in the top left, a constant plus or minus a constant times either sine or cosine. Now, the only difference between a sine and cosine is you kind of see how these are pointing like in the x direction. If it's a sine, it'll be a vertical direction for those. And depending on what the A and B ratio is what the different shape is going to be. But the good news is we're going to use the same method to graph each one of those. Now, our next type of curve are called rose curves. I'm not sure why they're called rose curves. They look a little more like clovers to me. But they're all going to have the form of either a constant times sine or cosine, and then a multiple of an angle, like cosine 4 theta or sine 3 theta. Now these curves are only if n is bigger than or equal to 2. If n is 1 here, you actually get a circle, an all-centered circle. But for these, the number of petals that you end up with is either going to be the number that's the multiple of theta or twice that. And what do I mean by that? Well, if n here is an odd number, you're going to get that many petals. And if n is even, you're going to get twice that many. So here, if n was 4, we'd actually have 8. See over here, n is 3, we end up with 3, same idea. N's 5, we'd have 5, but n is 2 is 4. So the idea of it's an odd multiple of theta, you get that many petals. If it's an even multiple, you're going to end up with twice as many. All right, so now that we know what the basic equations are that generates these graphs, let's go ahead and see if we can graph a few of them. All right, now that we know what to expect from our polar graphs, let's actually see if we can just graph a couple of these and see our different methods. Let's start out with, I don't know, r is equal to 2 cosine 2 theta. Okay, the first thing we want to do is be able to identify what type of curve this is. So since this is just a sine or cosine with a multiple angle, this is going to be a rose curve. Spelled wrong. Rose curve, and we need to know how many petals there are. So since in here the multiple is even, we're going to have 4 petals. Okay, that's really all we need to know to solve this. Now, here's the idea. If I'm trying to draw some type of rose or clover type pattern, notice this. If I knew where the tips of all the petals were, and I knew that there was 4 of them, let's say that I know that those are the tips of 4 petals, can I draw the picture? Yeah, that's all we need to know, is because we know we're going to have a petal there, petal there, petal there, and a petal there. Now, that's enough to draw the picture, but that's actually not how the picture would be drawn if it was to draw itself. We'll see how that actually works out here in just a second. So the idea for drawing a rose curve is all we have to do is find the tips of all the petals, and we'll know what the picture looks like. So what do we know about the tips of each one of those petals? Well, those are the tips are the farthest away from the origin as possible on that curve, which means r is as big as possible. So here's our equation for r. So what's the biggest r can be? Well, the biggest r can be is when cosine is either 1 or -1, right? Because that's as big as it can be in magnitude. So in this case, we want to know when cosine 2 theta is equal to either plus or minus 1. So when is cosine equal to either +1 or -1? Well, cosine's the x value when we're talking about our unit circle. So that would be when we're either here or here. So at either 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. So this is when this argument, anytime that argument is equal to any multiple of pi, which means that'll be true anytime we have any multiple of pi over 2. Okay, so now let's just list out the angles that will give us each one of our peaks. So where's that going to happen at? Well, we generally start in at 0 here. So our first angle will be at 0. Our second angle, let me go and put it over here. If n is 1, would be at pi over 2. If n is 2, that'll be at pi. And if n is 3, this will be at 3 pi over 2. Okay, so there's the 4 angles in which we're going to be the maximum distance away from the origin. What's that distance going to be? Well, if theta is any one of these angles, or actually any of these angles, what value does this have? Well, if we plug this in, let's doing this. If theta is equal to 0, then r is equal to 2 cosine of 2 times 0, which is 0. Cosine of 0 is 1, so that's 2. If theta is equal to pi over 2, that's our next angle, r is equal to 2 cosine 2 times pi over 2 would just give us pi. That'll be negative 2 then, because cosine of pi is negative 1. If theta is equal to pi, r is equal to 2 cosine 2 theta, so 2 pi's. Cosine of 2 pi is 1 again, so that's 2. And if theta is equal to 3 pi over 2, our radius will be 2 cosine. 2 times 3 pi over 2 would be 3 pi. Cosine of 3 pi is negative 1, so we get negative 2. Okay, now here's the difference between the two. I'm going to show you when you're just sketching this by hand what you need to do and what's actually happening here. So let's take a look at what we're talking about. First off, since we know all the angles, I'm going to do this real quick. I'm going to erase and we're going to start over. I could just say, well, I know it's always going to be a maximum of 2 away, either positive or negative, doesn't really matter. Just go to each one of these angles and at a distance of 2 away, 2 away, and 2 away. You don't need to put those 2's on there. I'm just showing you that's the distance away from the origin. Those were all the tips of those petals are going to be. So all you need to do is just draw the petals. And you're done. And most of the time that's really all you need, but that's not how this picture itself is drawn. Let me show you how the picture is drawn. Let's go by our points. Our first point, when theta was 0, we're at 2. So the first point here is that one. I'll put a 1 next to it. So think about this. When theta is 0, we drew out to this point. So we drew that point there. Now we're letting theta get bigger. So from 0 to pi over 2, our point goes from that point to what? At pi over 2, we're at negative 2. Now this is where it gets tricky. Now we're looking pi over 2. We're looking straight up, but we're going to go down negative 2. So that's our second point. Okay, so here's what we have so far. Now this is where it gets a little visually tricky. Remember, our angle is measured this way. So as theta gets bigger, we're drawing the graph. And when we draw the graph, we're drawing this part of the curve, but we know we go to this one next, so we're heading down to there. So from 0 to pi over 2, that's what we've drawn so far. We've gone up like this, so the radius has gone out and come down to there. Our next point, when we're at pi, we're at positive 2. So now we're looking in the pi direction, and we're going to walk 2 steps that way. That's our third point. So remember, our angle has gone from 0 to pi over 2. That gave us this part of the curve. Now we're going to go from pi over 2 to pi. So I guess I should do it this way. So now our angle's going this way. But notice, to draw this piece, our radius is negative, so it's actually drawing out this way. And then we get over to an angle of pi. So that went from here, kind of like think about my elbows drawing the back part, until we get to about there. Then we start drawing the positive portion of the curve. Okay, so our last point is at 3 pi over 2, negative 2. So now we're looking 3 pi over 2, we're looking straight down, but we're going to go in a negative direction, so we're going to go up negative 2. So that's the point, 3 pi over 2, negative 2. So think, now as we move from pi to 3 pi over 2, our angle is going to go through here and draw that portion. Now, of course, we don't have another angle to do. We could keep going down here, but you notice that gave us all 4 of our tips. Remember, that's all we were looking for. If you did the next angle at, what would the next angle be? It would be at 2 pi. The same thing would work, and we would get the next point would be this exact same point here. So this was our 4th point. that would be kind of the fifth one, which is the same one, which means as we go from 3 pi over 2 to 2 pi, right, from 3 pi over 2 to 2 pi, we sketch out that piece right there. All right, so visually it's a little tough to see how polar curves are drawn. Just remember your angle's progressing from 0 to 2 pi normally around here, and your radius is going out and changing distances. Remember, your radius can be negative as you go around. So just visually so you can kind of see this. For our first one, we went from 0 to 2. So we went from our first point to our second point. They went from 0 to pi. Technically, this part of the curve was drawn with a negative radius, because from here to whatever that is when we went in right there, we had a positive radius, then our radius was 0. Then when we finished going up to pi over 2, we drew out the negative part. All right, so those are your rose curves. Technically, if you're just doing a very, very quick sketch, all you have to do is just find the 4 tips of what angles it happens. It always happens when the trig function is a maximum at either plus or minus 1. Find all the angles that give you that. Put all the tips out there, whatever angles they are, and just kind of sketch it. You don't have to worry about what order it's done in. However, if you actually want to see how it's drawn, you do have to do something like this to kind of show the order. All right, let's take a look at another graph, maybe one of those Lemicons, and see how we're going to draw those, because we are going to do a slightly different technique. For our rose curves, we go after the tips of those, but if we're doing something like a Lemicon, like 1 plus 2 sine theta, we're going to do a slightly different method. Here's what you're going to do. First, you're going to say this is a Lemicon. And we had, the picture, remember the picture I showed you, had 4 different types. It had kind of like one with the inner loop, one that kind of comes in and touches, and then other ones that are just kind of bent in. We actually don't care. Our picture will take care of that for us. So if we're going to do this, we're going to make a table of values, theta and r. Now all you're going to do is pick your quadrant angles for this. So we're going to go 0, pi over 2, pi, 3 pi over 2, and 2 pi. For each one of these, we're going to plug it in here and see what our radius is. I'm going to do this kind of quick. So let's see, the sine of 0 is 0, so our radius is going to be 1. Excuse me, sine of pi over 2 is 1, so 1 plus 2 would be 3. Sine of pi is 0, so that's going to be 1 again. Sine of 3 pi over 2, sine of 3 pi over 2 is negative 1, so 1 minus 2 would be negative 1. And sine of 2 pi is 0, we're back to 1. Okay, so go through, make sure that you can find those points on your own a little bit slower. Let's see how we actually plot these points. Now again, plotting points can be a little tricky. First one, we're looking at the direction of 0, theta equals 0, so we're looking down the positive x-axis, and we're going to go out 1 step. So let's just say that that's 1 step right there. Now we're going to look at pi over 2, so now we're looking straight up, and we're going to walk 3 steps out there. Now I'm not going to put little hash marks here, but I'm going to say it goes a 1, 2, kind of 3 steps that way. I don't know if y'all can see that little tiny 3 on the video. Now we're looking at pi, so I'm looking down the negative x-axis, and I'm going to walk a positive 1, so kind of same distance this way. So I'll walk a positive distance 1 there. When I'm at 3 pi over 2, so now I'm looking straight down, I'm going to go negative 1, so that one's actually up here. So that's a distance of 1 there. And then again, if 2 pi, I'm looking straight down the positive x-axis, that gives me this point here. So I'm going to get rid of all of our step sizes. So what shape is this? Well, we know our cardioid shapes, like I said, the picture I showed you either have kind of this loop in the middle, or kind of an indent in the middle, or just kind of a slight indent kind of thing, and a little bit closer there. So which one would that be? Well, the way that I'm looking at this, it kind of looks like, by the way, this spot right here, if you notice in the picture, and the one that's kind of right there, always ends up at the pole or the origin. By the way, I don't think I've mentioned this in the past because we weren't graphing yet. When we're in the polar coordinate system, the origin's called the pole. So this would actually be the one with the inner loop to it. So think about it. How would we draw this? Well, this would actually come through like this. and we would get that kind of picture. So to graph your cardioids, or your lemicons, in this case, the kind of cardioid type shape, all you do is pick your quadrant angles, plot the points, and then figure out which one of the four shapes that we have it's going to be. So not too bad. Those are fairly easy to sketch out real quick. All right, now that we have these new graphs, we're going to start doing a lot of the same things that we wanted to do in the past, like finding tangent lines. Well, to find tangent lines, let's say I wanted to find the tangent line to the curve somewhere right about there, we're actually going to go back to the idea of rectangular. So the slope of this would be dy dx. The problem is, as of right now, to draw this picture, we said r was some function of theta. In this case, it was 1 plus 2 cosine theta. So how in the world do we get from r as a function of theta to dy dx? Well, believe it or not, we actually already know how to do this. Because, if we assume that r is some function of theta, remember we know x is equal to r cosine theta and y is equal to r sine theta. Those were our conversions from polar to rectangular. Now, if the curve is actually r as a function of theta, that means that these two can be written as x is equal to that function of theta cosine theta, y is equal to that function of theta sine theta. So basically, here's the idea. I was able, because r is a function of theta, I was able to rewrite our definitions using only one variable now. So now notice both x's and y's are functions of another variable or of another parameter. And we know how to take the derivative of parametric equations. I know that dy dx would be dy d, whatever the parameter is, theta in this case, over dx d theta. So let's figure out what this is going to be. It's going to be a little bit messy since we don't actually know what this is. Now, if we knew what the function is, we would just put it there and actually find the derivative. So dy d theta. So if we're going to take the derivative of this, we're going to have to use our product rule. So that would be, since I don't know what f is, I'm just going to write it f prime of theta sine theta plus f of theta cosine theta. That's the product rule on the top. And on the bottom, dx d theta, the derivative of this with respect to theta is going to be f prime of theta cosine of theta minus f of theta sine theta. Okay, so that will give you the slope of the tangent line. So just like before, the idea here is, since we have our conversions from polar to rectangular, and since r is normally a function of theta, as long as we plug in what that function of theta is, it's very easy to find the derivative or the slope of the tangent line. Which means we can go and do things that we've found in the past, like how do we find horizontal tangent lines? Well, that's when this is equal to 0, right? That's when the derivative is equal to 0. Well, that'll be when dy d theta is equal to 0. How do we find vertical tangent lines? Well, that's when this is undefined, or when dx d theta is equal to 0 as well. Okay, so just something we already know from the past is just how to take the derivative in parametric form. Now, one more thing I want to throw up here real quick that we've seen in the past, but the formula is going to be a little bit different, and it is just a formula. Since we're drawing a curve, we have an arc length. How do we do arc length in polar? Now, since I've already shown you how we derived this formula a couple of times, I'm just going to say the formula. So let's say we're going to do the arc length. Now, the first idea is, remember when we're drawing a curve, we have, let's say we're drawing the curve. Let me clean this up just a little bit. Get this out of here. Let's say we were drawing the curve. Let me do a different color here so we can kind of see it. From, that doesn't work at all. Let's see, let's go to red then. From that angle to that angle. So if we wanted to know the arc length of that piece, Well, what you do is you say, well, we started some first angle theta, and we go out to whatever the big angle is, say beta. See, it's the angle that determines how far the graph that we've covered so far. So what we'd want to say here is we would find the arc length would be the integral from alpha to beta. That's just over what angle we were sweeping out at the time. The square root of r squared plus dr d theta squared d theta. Now, of course, if r is equal to some function of theta like it normally is, you can just plug that in there, so that would be f of theta squared, and that would be f prime of theta squared. Just a different way to write it. Now, it is just a formula, so make sure that in the homework that you can apply that formula. So drawing our polar curves, you do want to make sure that you know what the picture is before you get started, or at least close to what the picture is. And then if it's a rose curve, you find the tips of the petals. If it's a Lemicon, then just plot your 4 quadrant angles and see what shape you end up with.